Good afternoon. It's good to see that all of you survived the quiz. The performance was generally quite good, and there were some systematic errors for which we will prepare some slides and they'll be discussed in your recitation sections tomorrow. Today we want to see if we can actually implement the programmable machine you have learned so far, RISC-V, build actual hardware to realize it, to see if it can all be done in hardware. And it's going to be easier than you think. So let's get started with this. So I think this kind of an interpreter should be embedded in your head by now, that what does it mean to execute the instructions of a program. Program has a program counter, so you go to that location in the memory and fetch the instruction from there. Then you decode the instruction so that you find out exactly what you're supposed to do with that. And then you execute the instruction. So if it's an add instruction, you add it and you produce the results. And then in the last stage, you actually go and update the register file. You actually go and update the state of the machine. And you do this repeatedly. So updating the state of the machine implies that you're also updating the program counter. And if you have updated the program counter, then when you go and fetch next time, you'll be fetching a different instruction. So this is what you do repeatedly. And now we have to build a sequential machine that actually does all this, right? So what we'll do is we'll start slowly. We'll look at the components of this machine, and then we'll put them together. You have already seen some of these components, right? Okay. So the component that you have already seen, actually implemented in lab 2, is ALU. It performs all the arithmetic operations like add, subtract, etc. And you wrote a combinational function for it, and this combinational function could be translated into gates. And from now on, instead of writing all the time bit 32, because it's a 32-bit machine, we'll just write word. And somewhere else you would have described that the type def for word is 32 bits. All right? And similarly for ALU function, you have to say what functions are supported in this ALU, in this hardware, and these are add, subtract, and or XOR, shift, etc. that is given over here. So this is exactly what you implemented in lab 2, and it's a very important part of this machine of any CPU. It contains an ALU inside it. We also need a similar ALU for doing comparison operators. So the only difference is that this one returns a Boolean instead of returning a 32-bit value. So you take two values and you perform some comparison, and then it returns a Boolean. So what kind of comparisons do you perform? It can be equal to, not equal to, less than equal, less than unsigned, greater than equal to, etc. So it's very straightforward to implement. By now you are all champions. You can write this function, which is simply a case statement, right? So you are given the branch function, its type I showed you on the previous slide. So the case statement is a case on the branch function. If it's this, if it's equal, then on the right hand side you have to generate a circuit which says A equals B, which is a pretty trivial circuit to generate. So the whole ALU is, this one is as easy to implement as the ALU you saw earlier. Now we come to the next component, which is also very, very important in machines, and that is called a register file. As the name implies, it's nothing but bunch of registers, which you are quite familiar with. The only difference is here all the registers are going to be controlled by the same enable signal, right? So you will go and write into a particular register inside it, and we also control it. So if we have a register file with 32 registers, which is what we need for implementing RISC-V, we can't just go and read all of them at the same time. So there is a restriction of how many registers you can read at a given time or how many registers you can write at a given time. often referred to as the number of ports in a register file. So this is a 3-ported file, 2 ports for reading and 1 port for writing the register file. And these methods are easy to understand. I have not shown any red and green signals for the read ports. And why is that? When do you need a red line? When do you need an enable signal? When you want to update something, right? So when we are reading, we are not updating anything, we are just simply reading. So there is no red line needed for the read part. But on the other hand, for the write part, of course, you are writing in a particular place, and that will be done only if the enable is on. What about the green signals? What do green signals tell us? Ready. We did not have green signals for registers, right? Why? Because it can be read anytime. It always contains a value. You can read it whenever you want. Same thing is true for register file. It can be read anytime, right? So that's why no signals are shown over here for doing the, I mean, all 3 methods are always ready to go. So this is the interface for the register file, and let's see if it makes sense. And as you can see, I have named it reg file 2R1W, you know, 2 read ports, 1 write port, and therefore it has 2 read methods which have been named RD1 and RD2, and you just have to give me a register name. So that's the index. And how big index is? It's 5 bits because we have 32 registers. And this register file store words, so therefore the data being returned from it is a word as a consequence of the read operation. Similarly, for write, you have to give me the name of the register, the index, and a value to be written in. Yes, please.
So how many registers does this register file have?
So I think this is not stated clearly on this slide, but when you make the register file, it will always have 32 registers.
And that's why the index is...
Right. But I could have done it differently, but we only instantiate this register file, so I don't want to clutter the types. Okay. Why has this signal come on? Anyway, all right. So register file implementation, it's pretty straightforward, right? So very first thing I'm doing is I have a vector of registers. Now this is slightly subtle that there is a register M there, replicate M, because you want a new register. It's not the same register being created, and I won't get into the details of it. Just copy it. Anytime you have to make a new register, use replicate M over there. Otherwise, this vector will, all of them will point to the same thing, right? That's not what you want. Okay, and you have 32 of them, and each one of them contains a register. Okay, and we have 2 methods. So RD1 is what? It's simply reading from register file the index you are specifying in there. And similarly, for writing, there is one minor caveat that RISC-V says register 0 always contains a 0. So we check. If you're trying to write into register 0, then we don't do anything. We ignore it. Otherwise, we just go and write the data you have given me, and that's what is shown here, right? So you're writing the data into this register file, but this is preventing you from writing into register number 0, which always contains a 0. So register 0 is hardwired to 0 and cannot be overwritten. Another very interesting thing to think about is, so you have this module, a register file. It has 3 methods, and it's very natural to ask the question, can I use all 3 methods simultaneously? Obviously, that's what we want to do, right? So these methods can be executed simultaneously, and then there's the next set of questions that arise, which is, if I'm reading and writing the register file, what value do I read? Do I read the value you were just writing, if I happen to read the same register, or do I read the old value from it? And based on your experience with the register, what do you think the answer is? You read the old value, right? You do not read the new value. So whatever you write in the register file will only be visible in the next cycle. It's not visible in this cycle. All right, so this is something which is quite important to remember. So in technical jargon, which we'll pick up later on, I often like to say it like this, that if reads and writes are happening together, then the reads appears as if reads happened before write. Right, happens before. You should read that less than sign as happens before. All right, not a big deal yet, but just remember that. Okay, this is the same property, by the way, for registers. All right, now we have magic memory, and as the name implies, it is truly magical because no real memory is like this. So what I'm calling memory here really behaves like a register file, right, in the sense that, and that's not true for any SRAM and DRAM, which you will learn a lot about shortly. Okay, so reads are combinational. You can do them anytime you want. And write, if enabled, is performed at the beginning of the clock edge. This is exactly how a register file behaves. So at the level of programming, at the level of design, it may be a different beast altogether, this magic memory, because it's going to be much, much bigger than a register file. But for us, it behaves more or less exactly like a register file. All right? The only difference here is register file had 3 ports, 2 read ports and a write port. Here, this whole system has only 1 port. So all the reads, writes go through the same port, which means the interface of it looks somewhat different. All right, so let's look at the interface of this thing. This is what the interface will look like. So you have an op, which is specifying whether you want to read or write, load or store, right? And then you have to always supply me an address. And in case it's a load instruction, you just supply me the address and it'll get an answer back, right? The data. In case of a store, you have to actually supply the data as if it's going in, right? And in case of a store, no response comes back. You just write it and you just assume it's done. No response, void is the response for this. Written any time so that the guards are always true, again not shown. And here is the interface. This is relevant for us because this is what we'll be using. So I say interface of magic memory is that it has only one action value method, right, which we call request. And you're sending R in, and if you look at the R, it has op, address, and data word, and the opcode can be load or store over here. And if I was trying to do a load operation, then of course I don't have to specify the data part because that will be coming out of it. Data is what will be returned, when the magic memory functions. And similarly, if you have a store, then you have to supply the data along with the address, and it returns nothing. It returns a dummy, right? You could have written underscore there if you want. It can't be used for anything. Okay. Now we come to the next major part. So far we have seen ALU, which is a machinery for actually computing, right? Given 2 numbers, it adds it. Then we have seen this tiny storage called register file, 32 of them. Then we have seen potentially a much bigger store, which we are calling magic memory today, right? And the main thing, the difference was it has only 1 port. All the reads and writes go through that. And now let's come to the next major part, which will involve some work at our end, which is instruction decoding. Now, an instruction can be executed only after each of its fields has been extracted from the 32-bit number that you read from the memory. Because given a PC, all you get is a number out, 32-bit number out, from the memory. And now you have to say, what does it mean? That's what instruction decoding is. What does it mean? And this turns out to be a very interesting question. Instruction or may represent an instruction not supported by our implementation. So basically what I'm warning you is I can also put garbage in and say, please decode it. And then you are supposed to come back and say garbage or unsupported or something like that, right? So that's a possibility in this. The other thing we will recognize, there's a purpose to this. Why are we decoding it? Because we want to execute the instruction. We want to carry it out. And we will find that many instructions behave almost identically all through the machine. The only difference is you do something slightly different in the ALU. Otherwise I can give you a parameterized execution of a class of instructions which do all the same thing, but at the very last moment when we have to call the ALU, we'll call it with a different function, right? So we group instructions according to the similarity in their decoding and similarity in their execution paths things. Now RISC-V is practically as simple as it gets when it comes to instruction sets, which is something good, right? Because we understand a lot more about instruction sets than we did 50 years ago. So if you go back to early instruction sets, they were very complicated. And the one that survives till today, which is extraordinarily complex, is x86. I mean, it's really just to write the decoder, if we were doing it in this class, it might take, half the semester, maybe not that long, but quite a long time to understand how instruction decoding for x86 works. Okay, so let's do an example. This is very important for you to understand. How do I, because if I just gave you this, what does this 32-bit number mean? You should have a heart attack. You say, whoa, tell me more, And you immediately, the only way you can understand it is you need some reference manual for the instructions handy, right? And we have given you a cheat sheet or something, one-page sheet. Without that, you absolutely cannot decode. And the first thing you will learn is that reference manual specifies some fields, but these fields themselves are there is dependent coding going on here. So very first thing we do is we read the opcode, which is the lowest level bits, right? Lowest level 6 bits, 7 bits, how many? 7 bits you read over there. And then if you consult the reference manual, it will say, if you see this bit pattern, this is a class of instruction which is called R type or opcode type, etc., etc. But the most important thing from our point of view is the moment it's like that, then it tells me how to read the other fields. And it tells me, oh, if it's an opcode, R type of instruction, then the rest of the fields should be interpreted as follows, right? So there is going to be 2 sources, RS1, RS2, and there is going to be an RD field into it, the destination where you'll be writing. And there is this funct3 thing, which will tell me exactly what operation ALU has to perform, and funct7 field, etc., etc. So we have to understand the meaning of all these fields. The only thing that is obvious in this case is that RS1 and RS2 and RD, as the name implies, have obvious meaning. Okay, so let's look at it. So funct3 is 0, 0, 0. Again, the reference manual will tell you that, oh, this corresponds to the add instruction. Good, so now we know we have an add instruction. And what does 0, 0, 0, 1, 1 mean for destination? This add field, this add instruction is going to modify register number 3. Good. And what are the sources? 2 and 1. So far, so good? And you can see in this case, we didn't do anything with funct7, right? We are not using that part at all. So now, what we will do is we'll say, what you want to do whenever you see this, and this is the so-called the semantics, the meaning of this instruction is something like this. Let's see if this makes sense. It's saying read the register file, the second register and the first register, add them together. How? By calling the ALU function, and whatever results you get, where are you going to store it? In X3, so that's what register file dot write 3, right? We are writing in the third place in the register file. And just by writing this phrase, the implication is that both the reads and the write are all happening at the same time. And we have all agreed that when we read and write at the same time in the register file, we first read the values and then later on we update it, which will only be visible for the next instruction execution. Yes?
Why is it necessary to have read1 and read2 as separate functions to do the same thing?
Because you want to do two of them simultaneously.
Would we not be able to do like rf.read2 and rf.read?
No, because that's a very good question. So in software, you might have been able to do that, right? So yeah, it's a function, call it, with that. In hardware, if it's already in use, the port is already in use, you can't use it. You can use it in the next cycle, but not in this cycle.
So if we want n simultaneous read calls, we would
We need n ports for that. Did everybody get that? Right? That if it was software, the functionality of read is the same, whether it's RD1 or RD2. All we are emphasizing is that there are two ports which can be exercised in parallel. At the same time, you can do both the reads. Good. Okay, so now we have to be able to decode all 32-bit numbers that you will throw at me. So let's study our instruction set again. And if you look at all these instructions selected from the ISA, you will discover that all these instructions have that quality. You read source RS1, RS2, and you do something to the destination RD. The only difference in these instructions is what goes on in ALU. So we will call all such instructions in a category called op. And whenever we have the op category of instruction, it will have the following fields. It will have funct thing in it, and the meaning of funct is this is the opcode we are going to be feeding to the ALU, and it has a destination and two sources. Good. All right. Now there is another class of ALU instructions which are very, very similar to the first ones. The only difference is instead of the one of the sources, the second source actually is coded in the instruction itself. Instead of reading it from the register file, it's an immediate operand. It's specified in the instruction itself. It's a conceptually very straightforward idea. You'll be surprised, though, how tricky is the coding of that constant, right? I mean, people want to use every bit available in the 32-bit instruction so that they can write the biggest possible constant in the instruction itself. So what RISC-V designers have done is they have simplified all decoding. I mean, every field is almost never changes. RS1 is always in the same place. RS2 is always in the same place. But man, when it comes to finding the immediate operand in the instruction, it is the most complex thing, right? And you will see an example of that, how we will put together a constant that is in the instruction itself. But right now, from our point of view, really, all these instructions will code the constant also in the same way. So they're very, very similar. All these instructions will be decoded in a similar way. All of them, we can form the operand, we'll feed it to the ALU. The only difference will be what operation we perform in the ALU, which is going to be specified by func3. So the only difference between this and the previous one is here we have to compute this immediate thing which has to be constructed. Okay. Now just to remind you that how complicated decoding can be, let's look at this one. Again, we pull out our ready sheet for figuring out what instructions mean, and it says opcode, this means it's a branch type, B type of instruction. Good, all right, I can understand that. All right, and func3 is 001, which according to the reference manual, it's this opcode B branch on not equal to, right? So when two values are not equal to, you'll do something, and you are specifying two registers that you're comparing. So that is RS1 and RS2, X1, X0. Are you all with me so far? So the only thing left to specify now is, what should I do if this is true? If the comparison is true, I want to jump somewhere, right? That means I need to compute an address where to jump to. And where is that address coming from? And that is also encoded here as an immediate operand. And this is going to do a number on you. So we have, let's look at what we have here. So I have extracted the 12 bits that are in the instruction itself, and they will form the bits 1 to 12 of the immediate I'm trying to construct. Ultimately, I want to construct a 32-bit intermediate, right? Okay, so let's see how these 32 bits are being gathered. Can anything be more weird? Right? Look at bit 1. Where is it encoded? Immediate 1 is, I'm getting mixed up here. Okay, so this is bit 11. Where is bit, this is bit 12, and this is 5 to 10. What did I miss? 4 to 1, okay. Do you all see it? I mean, it's a very, very simple idea, but why it's like that, don't ask me. I mean, somebody spent a lot of time trying to design this stuff. Who knows what the hell they're optimizing? But believe me, it's a good design, right? But now you have to do the lab. You have to actually write a decoder. So you have no choice but to understand all this, right? Exactly how to put together this constant. Okay, the story is not over. So at least 12 bits we extracted from the instruction itself, and that's just wires coming out. But now reference manual tells you that when you see something like this, then immediate 0 will be 0. And by the way, the rest of the bits are sign extended. So if you think of it like that, then after some gyrations, mental gyrations, you'll be able to figure out that this 32-bit number that I have is actually -4. Just see how many gymnastics we had to go through to encode -4 in the instruction itself. Okay, you don't want to do this by hand. There are programs called assemblers. You write in some high level, jump to such and such, branch such and such, right, to this label. And some computer program goes and puts all the bits for you in there. And now what we are trying to do is decipher it the other way. Yes?
Why only the first bit is already set to 0 if all addresses in memory are 4 by 4?
Right.
So why is it only the first one? I can add 2 of this,
That's a good question, and I don't know the answer. You're saying we jump to words, so why am I only zeroing out the lowest bit to 0? We should probably zero out 2 bits. Yes?
The RISC-V supports half words as well.
Okay, you got the answer.
Use them.
RISC-V also, yeah.
It's also outlining the slides. It should be 1, 1, 0. So
Sorry?
the last 4 bits should be 1, 1, 0, 12.
1, 1, 1, 0.
Because that's 12 to 1, right? So then the full number is 1, 1, 1, 0, 0.
Right. So I forgot about half words, right? So RISC-V actually has, we are looking at only one instruction encoding, but it has actually 2 instructions encodings. It also has a compressed format so that you can store the same instruction using fewer bits, which is very, very important for embedded applications. But what is important, as Silvina pointed out, is we are not implementing that in this class, but not all data types are 32 bits. We also have half words and bytes, etc. And we can specify operations on half bytes. And apparently we can jump to half words also, right? So that's why this instruction is allowing you that possibility. Okay. So the meaning of this instruction is it's a branch instruction. So first we have to compute something in ALU, and depending upon what comes out of ALU, then either you will go to PC will be PC minus 4, or it will be PC plus 4 is the normal case, right? Is this clear to everyone, right? And the thing I want to remind you again is it's always very straightforward to find out RS1, RS2, RD, etc. It's also not so difficult to find out opcodes, though in some cases it'll get tricky. But the most complicated part in decoding an instruction is to put together these constants. Okay, good. So these branch instructions, fortunately for us, they all encode the constant exactly the same way. So we have grouped them together. We'll call them the branch opcodes. And in this case, what we will get is a branch function, RS1, RS2, and this kind of immediate value, I've just labeled it immediate B, because this is the branch stuff that comes out. So we have taken care of quite a few instructions, right? Op instructions, which were doing something in the ALU, then op immediate instructions, which were also doing something in the ALU, but they had a constant immediate operand. And now the branch instructions, and the remaining instructions are another 5 or 6 instructions, and they defy categorization. So let's put them each in its own category, because they all have different encodings inside it. Okay, so these instructions are jump and link through register, load and store instructions, and LUI, and this instruction was discussed quite a lot earlier, right? So these instructions are in a category by itself. I just want to focus on one thing, which is the memory instructions, the load and store instructions. Load and store instructions are such that you always have to first compute the address that you want to access in the memory, right? So there is a phase in the execution of any memory instruction which is called computing the effective address, right? It takes some time because there is also, it's often off PC, and it's always involves immediate operands which are stored in the instruction itself. So we have to just construct that part, and you have to be cognizant of it when you're doing it. In other words, if I'm the high level point I'm trying to make is, what is the purpose of the decoder? Unless I know what this instruction does, I obviously can't implement it, right? So the very first thing you do is fetch the instruction, decode it, right? And now from programming point of view, from writing the program which will represent it, what I have to do is, we need this instruction decoder, we need a function to extract the category and various fields of each category from a 32-bit instruction. These are the fields we have already identified. Okay, most of them make sense to you. And functions for ALU functions, we have specified all these things. For immediate operands, we have huge variety of things. So we had immediate I, immediate B, and immediate J. In other words, every instruction is different type, is coding the constant differently inside it. So I've just named them. But the thing to remember is, given the constant, ultimately you're trying to build a 32-bit value. So there is a way specified in the reference manual of how that 32-bit value is put together, given the immediate value in the instruction itself. And the other thing to remember is, as I started this stuff, unfortunately, it's not so simple as saying, here is the instruction, here is RS1, here is this, here is the immediate operand. It's dependent coding, right? You look at the opcode first, that tells you what is the meaning of other fields, what is the meaning of other bits in the instruction itself. So what I'm going to do is, as we do in everything when we have to write it in BlueSpec, we define a data structure. And we're going to define a data structure for a decoded instruction. All right, so decoded instruction. And what I'm suggesting to you is it's going to be a structure which we haven't discussed, but it's obvious. It's like any other programming language, the software that you're familiar with, right? So you have a structure which has very many fields in it. So these are all the field names. So one field name is iType, right? What is the grouping it belongs to, essentially. And then ALU function and branch function and destination and source, etc., etc., etc. Right? These are the field names in a decoded instruction. And if you look at it the other way, if I look at any particular field, I have to specify the type. So when I write, ALU function, what is the type of it? So what you see on the left-hand side is the type corresponding to everything. Yes? So what is that? So for example, iType is op, imp, branch, LUI, JL, etc., etc., right? And, okay.
Yeah, what is the deriving that's
So that's the refrain in all time. Every time you declare a type definition, you're defining a new type, right? So you will discover that there are many properties you want, which you will have to write down. How is it represented in terms of bits? How is it printed? How is the equality determined on that? So instead of making you do all the work, you can say, please derive the following functions for me, right? So deriving will give you the bits representation. It will give you the equality function on this. And there are many other things it can do, right? So even if I forget to write deriving, it's always there, right? You have to assume that this is to make your life easier. If you don't write deriving, that means you have to write down the equality on that type. And they're so trivial to derive that might as well let the compiler do it for you. Okay, so when you have ALU function, you have seen this type, and similarly you have seen the branch type also in this. We have seen all this earlier. Okay, and remember, register destination 0 behaves, you can't, it always contains a 0, you can't overwrite it. Okay, now the only thing that is funny in this type is this one, right? Maybe type. If you are reading something, I don't care, right? Because reading doesn't do any damage. But destination implies you may go and write it. So it's very, very important for me to know whether you actually want to write or not, right? So for destination, we call it a maybe type. If it's valid, then it contains a destination. If it's invalid, then it doesn't matter what it contains, that thing. So we'll be using it. This is a very popular data type that people use, maybe type. Did everybody understand it? That you have something and you have a valid bit. And the value is valid only if the valid bit is true. Otherwise, it's meaningless at that point. Okay. So this is the function. You will be given 32 bits, and I say decode it. And what does it produce? It produces this type of thing. It produces a decoded instruction. And guess what is your next lab? Write a decoder, right? By now, all you guys are champions. I mean, you know how to write combinational functions, right? Straightforward stuff, right? But a lot of code, right? But that's what you guys are good at. Yes?
Where did you find the R index type?
Sorry?
Where did you define the R index type for source one, source two?
I may not have defined it, but you can define it.
How do you define that?
The index type, it'll be bit 5, right? So what you will find in almost all BlueSpec codes is you have a file which is all the types you write. outside, because they are shared, and you can have name conflicts. So you have to be careful in how you use that. But general rule is that you write all the types first. You don't have to, but that's how we do it. Okay, yes?
What is a structure exactly?
Very good point. So structure is simply, I'm building a composite. So I have two types, T1 and T2, right? And I want to build something bigger which has T1 and T2 in it, right? So what I do is I give them names. I say field name, ID1. So that means that's the name of the first thing. Field name 2, ID2, right? So now I know that my data structure contains two things in it. The structure is a data structure which contains two things. So I need to be able to put it together, and I need to be able to read out things from it, right? So the field names in it, which I was calling ID1 and ID2, are precisely the names that are given here. So when you have a decoded instruction, you can say, suppose the decoded instruction is X. If you say X dot RS1, it'll go and read that field, whatever value is in there. And that's what you will see. Okay. You must have seen structures in 6001, right? Okay, good. So this is lab 5. All right. Now we are on to business. We want to very quickly build our interpreter, right? Putting it all together. So make my interpreter, and this is a funny one, so let's ignore that we are saying its type is empty, right? It has no methods in it. Okay, but all the things are being instantiated over here. Okay, so now we have instantiated a PC, RF, IMEM, and DMEM. We have made all these things. And now we have to write a rule, which is the do interpreter. And what does the rule do? Does this make sense? Go and read the instruction from the memory. Remember, this is magic memory. So you give it and it gives back the answer. In this, so opcode is load, and PC's address is PC, and there is of course no data, because data is what comes back. What comes back is what I'm calling an instruction. And what is the next thing you do? Right? You decode the instruction, and once you have decoded the instruction, you will get a decoded instruction out of it, right? And what is the next thing I do? I read I can extract all kinds of fields from my decoded instruction, because it was a gigantic data structure. And once I have those fields, then I can go and read the register file. To read the register file, I need the source 1 and source 2 from my instructions that came out. And that has given me two values now, val1 and val2, right? That came out of the register file. And now the next thing, I pass everything to the execution unit. So I'm giving the two values I have just read from the register file. I'm giving it the decoded instruction I had, right? And I'm saying, and PC also I pass it in. No, I didn't pass PC in. Yeah, I did. Okay, good. So I passed everything in, and now execute unit will go and actually produce the values according to this instruction that I need. And once I get those values, so this is another gigantic combinational procedure, right? So once I have this, execute the type of executed instruction is also very, very similar to the decoded one. So you will extract from it itype, destination, data, address, and next PC, etc., because that's what you expect to get, when you execute an instruction. And now you say update all the state elements. So I write another procedure. I say, please go and update everything in it. So this is my high-level view of this interpreter, right? That, I fetch an instruction, I decode it, I do register fetch, I call the execute procedure, which produces all the values I need, and then I call the update procedure, which actually goes and does all the updates in it. Now let's quickly see what is inside the execute procedure. So you are passing me the decoded instruction, and you are passing me the values val1 and val2, and you're also passing the PC, because many instructions need PC value also in it. So you will just extract all these fields from the you're doing this all the time, right? You're given a data structure and you need to read various fields, so you should just write all of them out. Say, okay, this is the type, this is the RS1, RS2, etc., from it, whatever things, information you need from it. Okay, so now depending upon I type, remember, one I type was op. Does anybody remember what op instructions did? What did op class of instructions do? Fantastic, exactly. And that's what we are doing here, right? So we are calling ALU function, which you have already designed, right? You're passing val1, val2, and you're passing the ALU function. It will return some data. And the PC value you are computing is PC plus 4, because this is simply an ordinary instruction, no jump involved here. And what will happen in case of an immediate, op immediate? The only difference is now the second source is going to be the immediate value. Everything else is the same, right? So that's pretty straightforward. What else? Branch. Okay, so I'm passing the two values and the branch function, and if it turns out to be true, then I jump to PC plus immediate. Otherwise, I jump to PC plus 4, like the normal case. And similarly, let's ignore this one, okay? And let's look at the jump instruction. So in a jump instruction, again, you have PC, and it's an unconditional jump. Nothing complicated. And what do you have to do in case of load and store? Okay, so suppose it's a load instruction. Now you have to do some work. You had a value RV val coming out of the thing that is passed to you, and you have to add the immediate operand to it. And once you add it, now you have the address available to you. And you have to issue that address, so we will keep it for the update part, because if it was stored, it can do something else. So remember, what the execute part did for load and store instructions is it only computed the effective address that is needed to access the memory. It did not actually perform the memory action. It did not do anything to the memory, and that is the last stuff that we have to do. That what is this updating that we do? I will explain that in a second, but first let me just see this. The simplest case is of the op thing here. So if you have a valid destination, then you are going and writing the value in the register file. You're saying take out the destination from this thing and write the data in there. And if you have a load instruction, then I have to issue a request to the memory, and if I have a store instruction, I have to issue instruction to the memory again. Okay, so that's all that is going on in this case. And when you put it all together, then you get actually the interpreter, which is the hardware for doing this. So very quickly, what did we do? We instantiated all the state elements. Yes? We wrote one rule, and what did that one rule do? It repeatedly did something. It fetched an instruction. It fetched things from the register file. It decoded, and then it fetched something from the register file. Then it did the execute, and then it did the updates in the update part. Before you leave, I just want to show you one more thing. If you go back here in this thing, I want you to just focus on this. Normally, when I was passing PC, if I want to pass the value of PC, then I would have written 32, right? Whatever the value of the PC is. But here I have written a register PC. So what I'm passing into this procedure is not the value of PC. I'm passing the program counter itself into the PC. That's why the register. This is a little subtle, right? It's like saying I'm passing the interface for doing something to the PC, right? But it is so convenient, once you, because programming wise, if you don't like procedures, just copy this whole code and put it, in the previous rule I showed you. Because procedures have no meaning at runtime in BlueSpec. You always eliminate them at compile time by just putting the body of the procedure wherever it was being called. All right, good.